So we're up.
All right,
Okay.
Josh.
Hello.
Hello. So, should we get started? I don't think anyone else is joining. I don't know.
Yeah, I don't think either.
So yeah. So my plan for today was kind of kind of an introduction to introduce ourselves and
Sure.
discuss some topics and plan for the
Yep.
next week.
Okay.
So I think uh, should I call you Divya? Divya
Yep.
is it right pronunciation? Okay. So I think um, how do I put it? Who will start introducing themselves so that, or is it not needed? I don't know.
You want me to introduce myself?
Yeah, and then I will introduce myself, and if anyone else wants to introduce themselves,
Okay,
go
I'll
for
go with myself first. Okay. So,
it.
I'm Divya. I'm from India. Um, my background has been in mathematics. It's a long story. I've always been interested in math, and physics. Then I got disillusioned of education system. I tried to teach myself math, a bunch of stuff. Then I started teaching other people math. Then I started writing papers and stuff like that. So all in all, I've spent a bunch of time doing math. And over the last couple of years, I've tried to get into programming in a deeper sense. I've always been fascinated with computers. I've played with computers since I was a child. Um, but I never. So what happened is, like, when I went into maths, pure mathematics, I um, had this weird understanding that computer science is kind of, the application of mathematics. It's like the applied sciences, and I wanted to kind of restrict myself to pure science. So this is just me being a teenager. That's all it was. um, and that's why I kind of distanced myself from computer science per se. I learned a few languages when I was in grade 6. Like, I think it was the first was, God forbid, Python, and then I guess it was like HTML. But then I was like, no, this is all just people doing it for jobs. Um, and then I was like, I'm just going to do mathematics. So I just did mathematics for several years. And then I found, well, I was always connected to computer science. As I told you, I started using Linux. I started, doing all sorts of nerdy things with computers. I was always aware of which language gets used where, stuff like that. Um, until I came to functional programming. When I came to functional programming, I was like, okay, I can do my mathematical stuff, the logic, and all of that alongside computer science. So this seemed like, it seduced me into computer science once again. So, and then of course I did rediscover Haskell, went into it, um, and here I am trying to study the foundations of programming languages, or programming language theory, I guess. So yeah.
I see. Have a really interesting background. Um, so my background. So let me get started then. My background was I come from an industry. I haven't studied in university. I don't know that much math. I'm just your regular programmer. So what got me into uh, overall, I'm interested in functional programming, programming language theory, compiler engineering, and type theory alongside dependent type theory. What got me interested in was that I've never been satisfied with the way I write code. I mean, I mainly write JavaScript and Go in my job, in my daily job, day-to-day job. So I've never really been satisfied with it. I just couldn't sit in one place. I tried out a lot of languages, and then I discovered Haskell, Scala, Lean, and so on and so forth. And the more I learned about these languages, uh, the more I wanted to delve, I mean, deeper into them. Then I got interested in compiler engineering. So it all got started with functional programming, then compiler engineering. But as I was learning to, um, how do I put it? As I was learning how programming languages work at the compiler level, I got interested in programming language theory. There are some chats, some Russian chats in Telegram. So I read a lot of stuff there, and there are a lot of interesting people. There's tons of these chats. I don't know. I can then share some of them if you're interested, but they're all Russian. So yeah. Why? And I set myself a goal to learn these topics: functional programming, language theory, compiler engineering, and type theory, in order to one day escape this commercial programming and become a GHC or lean contributor. So yeah, that is whole background, I guess, or, like an overview or something. So yeah, uh, Charlotte, do you wanna about yourself?
Yeah, yeah. Hello, everyone. My name is Shahzad. I'm from the same country as Kay, from Uzbekistan. So I started programming about, I can say, 8 years ago, and I took more pragmatic approach. So I started by front end programming, and then switched to back end engineering. And for the whole path, I was dreaming about mathematics, more mathematics than the computer science, actually. And I also didn't go to the college, to the university, because I wanted to be independent from my parents. So I started working commercially. Commercially, I'm working for the 4 years, I can say. And I was always curious what actually functional programming means. And thanks to Kay, I started uh, understanding actually uh, how it looks like, what theories I can do. And I actually really, I can say, started getting into the functional programming type theory. It's like the hidden side of the programming world of the, yeah, IT, I can say. So yes, I'm constantly watching YouTube videos, reading articles, trying to read books, but it's not easy, I can say. It requires a lot of research. So basically, um, I can say that in the future, I want to become a researcher, a guy who's between the pragmatic side and the science side, I can say. Yeah?
Ah, compiler
S-
engineer then.
Maybe a compile engineer, maybe something else, framework crafter. or library crafter. Type
That's a good
This
theory
is
option.
and
wonderful.
PLG site
We
give me. Uh, I hope it will give more understanding, more ways to think about code, about libraries. Recently, I discovered a great library, and now I'm playing with it.
Yeah, this
Yeah, this
theory
is nice.
actually expands your horizons a lot. Like,
Hmm.
Yeah, and we three are actually pretty close. Like especially when Shagzod said he didn't go to university. Well, I went to college and I just I was like, no, I can't do all of this stupid stuff for 4 years and hope that I have learned something. So, um, so it's good that we three have this, self-directed approach to learning. That's also something that you see rarely. Um, yeah, so I'm glad.
yeah. So now then, um, so yeah, it's kind of it for introduction, I guess. So, but I'm not still sure about the format of the conversation. Like, I
Hmm.
have read up until the lambda terms modulo alpha equivalent, so
Hmm.
uh, 1.7th chapter. I kind of
Hmm.
understand these things. Data reduction, I implemented it already in the repository.
Hmm.
So yeah, I don't have much of a questions up until now because I mean, I've read up on these things before too. So yeah, I don't know how the
Okay.
format going to be.
Okay. So what I think is useful is um, okay. So you have done until 1.7. You said. Well, I've done most of this all last week. Um, what about you, Shagzod? How far have you been able to see in the chapter?
I'm still stuck at 1.1 because this
Okay,
formal thing is,
definitions.
the formal
Yeah,
definitions are pretty tough to understand.
no worries. Well, that's why we're talking, right?
Hmm.
All right. So I think what we can do is we can uh, set a time. That's first. How much time we want to do every time we meet, and we just go through each section. We go through each section, try to understand and discuss. I think that will be good. What about you, Kai? What do you think?
No, that's a good option. So we're gonna be reading during this meeting, yeah.
Yeah, we're not going to
Oh,
like read line by line, so we're just like going to take a section, and well, I can start by saying, okay, what I got from it and where I was stuck, and then we can continue from there. So uh, yeah, because like reading line by line is not going to be difficult because like these definitions, they're not supposed to be read. They're like supposed to just it's compact and you just understand it and move on. So you
yeah.
can't actually read much of it. Yeah. So
I
that's
have
that.
a
So do you think?
question, sorry.
So go ahead. Go
Uh,
ahead.
is it essential to um, practice it on formal prover, doing replicating all of these statements while you're reading the sections, chapters? Is it essential to
Um.
make exercises in, for example, lean or something similar?
Okay, so Kai obviously has been doing this.
Mm-hmm.
I have done stuff in Cork, and I could as well do in Cork. But my approach is more like I first understand the material, and the ones that seem interesting and important to me. I implement them in formal prover.
Mm-hmm.
So I would focus more on understanding and then implementing than first implementing, because implementing is just going to take a lot of time.
Mm-hmm.
So yeah.
Gotcha. So as a disclaimer, I am not good at Haskell and
Okay.
therefore not good at Lean, but I heard that Lean is much closer to the Haskell type systems thing. So yeah, I'm doing sometimes
Okay.
Haskell learning too, besides of this book.
No worries, no worries. I think, well, first of all, we should take the conceptual approach, as I said, like first
Mm-hmm.
understand like what exactly is being talked about, and then think about what to do in programming.
Great.
Um, yeah, that would be better, because if you don't have a conceptual understanding and you try to code it, most of the time you're going to be stuck. So, um,
Yeah, or implemented plain wrong. So I actually didn't understand substitution that good, but I
mhm,
implemented it anyways. But now I
mhm.
read up on it, I realize that my implementation is kind of wrong. So yeah, I
No worries, what
realized
happened?
it 20 minutes ago.
Yeah, no worries. Okay, so one of us needs to stream. I can. You're already recording, Shakzod. Stream in the sense like we can all look at the same PDF. Um,
Yeah, for sure. I
so
can stream as well, PDF one, or you may stream. I'm recording.
okay, you record, I'll stream. That'll be better, I guess.
Okay,
Yeah.
let's stick with recording.
Okay. Okay. Can you see my screen?
Yeah,
Yes.
Okay. Okay, so yeah, so this is untyped lambda calculus, and it's going to cover to what, fixed point theorem, right? So Kai said he has done until 1.7. Why don't we aim until alpha conversion or maybe substitution for today's session, and for next session we can do from 1.6 to 1.10.
all right.
Sure, I will
Okay,
catch up.
yeah. So so yeah, okay. So I'm just going to talk about what the first two sections have, and I will try to explain what I have understood. Okay, so we'll try to do that. I explain what I've understood, you explain what you've understood, and we try to fix whatever is the gap between. Um, okay, so what I understand when I see the first section is there is this kind of theoretical model being talked about for what a function is. Okay, so my experience with functions is from mathematics, well, also from programming, but mostly from mathematics, where a function is basically something into which you put in something and it produces something. Right? So there is a set of things that you can put into the function and a set of things that it can output, right? That's the general idea of the function. Now, what the author is trying to do here is trying to give a much more abstract definition of what a function does. So, for example, here he talks about the function x squared plus 1. Now, in mathematics, how I will go about this is that, okay, there is some f of x for which every time I put a value of x, I get that value squared plus 1, right? So if it is f of 2, I get 2 squared plus 1, that is 5, and so on, right? Um, but what lambda calculus does, or what this method does, is it takes an expression. It doesn't talk about the function first. In mathematics, in conventional mathematics, we talk about functions first. You first determine what a function is, and then you determine the expression for that function. You think first about the function and then about the expression. Here we first think about the expression, what the expression is and what the variable is. So this is an expression which has some operator and some variable and some numbers, right? Um, so this is just an expression. And what lambda calculus does is whenever you have an expression which cannot be immediately calculated. So here's the difference. You can calculate immediately what is 3 squared plus 1, which is just 10. But you cannot immediately calculate x squared plus 1 because you don't know what x is. Right? X is an abstract concept. X is some abstract idea which needs some value for this expression to be computed. And to give notation to this abstraction, we have the lambda. So lambda x means that you have an abstract concept in this expression that is x. So that's what it means. It means that in this expression, you're talking about some abstraction. You cannot have this computed concretely because you have some abstract concept x, and that is just lambda x. That's how I understand it. In conventional mathematics, what it means is that it takes x to x squared plus 1. But when I think about it in terms of lambda calculus, what I think is x squared plus 1 is an expression where x is an abstraction. Okay, does that make sense? Any thoughts?
Yeah, it does make sense. Also, what I understood was that I read that a bit on lambda calculus with types 2, and that
Mm-hmm.
is in that Alonso Church intended it as to be a foundation for mathematics, but
Right.
it had some inconsistencies. So it is mainly used as a model for computation. As
Correct.
yeah, so I understood it like this.
Yeah, makes sense. Makes sense. Yeah. But I think this is also something that this happens in mathematics and logic. You realize something only after you have like gone further. It's like recursion. You do 3 steps and then you realize what you did in the first step.
Yeah,
um, I realized this, as I did layer sections, that like numbers or like these variables don't mean anything. What means is like what this represents. This just represents an abstraction, and that's how you should treat it. Because I was like thinking in terms of real analysis, that yeah, x squared plus 1 is like a graph in the second quadrant, stuff like that. That kind of stuff doesn't help. You should just
yeah,
treat it as an abstract expression. So yeah, and then obviously they talk about some examples, some notation, and yeah, the notation is that you represent it like this. It's like lambda x dot x squared plus 1 means you have this function which is going to take the input 3. So every time they have parentheses, it means they're applying something to something else. So this parentheses, this means this thing is getting applied to this thing. So yeah, that makes sense. Um, yeah, I think the this stuff is uh, that makes sense.
Yeah, I can say that I'm coming from purely
Mm-hmm.
programmatical background,
Mm-hmm.
and not the mathematical. So
Mm-hmm.
it is very obvious to me that it is an abstraction, and I'm thinking that it is a function in my, it's an function expression in my programming language. I'm crafting, I'm
Right.
writing it. So yeah, it doesn't mean anything. And also speaking JavaScript, it even can be strings or whatever else. So it is really abstract.
Right. Yeah, you really need to this is what the first chapter does. Everything that you have been used to about computation, forget it. That's what I did. Like whatever I was used to in my mathematics, I had to forget it, and I was like, okay, this is just symbols that try to make sense according to some rules. That's what you need to do, I think. Um, because you can't always find concrete examples. If you try to like find a lambda term in terms of a real trigonometric function, it's difficult to do that. So yeah, this is abstract.
Yeah, I had the same concept when I was trying to understand category theory, and
Uh-huh.
was frustrated because there is no single example which I can think
Yep.
about it. So it is very, very abstract.
Yep. Yep. And like what I say to the people I teach category theory, um, it's going to click at some point. That's what I can assure. But when it will click depends on the background you've had and at what point your intuition kicks in. Um, so, so yeah. So that's I think that's why we're doing this meeting. We can help each other's intuition kick in a bit. Yeah. But yeah, that's basically lambda calculus. You're trying to express these methods, these ways of doing things in a very abstract manner. You don't want to assume anything. You don't want to assume any structure, any number system, nothing. No assumptions. It's just variables and expressions and abstractions. That's it.
So if we going to sum up, there is not the variables are things. When you mean things, thing is not the value. It can be anything. So you can put substitute the variable with anything,
Yes.
including variable.
Yes.
Yeah, including values. Sorry.
Yes. Yes. So variable is basically um, like it acts as an abstraction for direct computation, right? So what can be valued is like 1 plus 1 that has a value that is 2. But if you want to generalize 1 plus 1 or plus 1 as an operation to a number of things, what you do is you take a set of things that you plus 1 to, right? So it's like 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, right? So now what you do is you're like abstractly creating a way of adding plus 1. And then you just like, satisfy some properties, and then it becomes an abstraction. It becomes a successor function, basically, right? It just gives you, for any number that you put into it, it gives you the next number, right?
Yeah, that makes
So
sense.
yeah, yeah. So you start from concrete, and then you build to more general and abstract stuff. Yeah, yeah. That's the goal of lambda calculus. But okay, so now next to essence of functions. Do we should we do turns? Me one section, then on someone else some other section.
Sure, if you want, I can do that too. Or, but I don't know. We
That's
can
fine.
try it out. But I think you're a really good speaker, better than me for sure.
Okay, so here's what we'll do. I will start this section, but we need to have some discussion because I don't want this to be my class or something, right?
Yeah, yeah. So
So
if you want, I can talk about the uh, 1 point second. the essence of
Sure.
functions. So, mm,
Go ahead.
so that all right. So here we're already in this chapter where it is introducing the structure of that of this anti-Planck calculus or on the constructs which it has, as you have mentioned, abstraction and application, and is also talking about the how do I put it, actions on them, like a better reduction on all the things. So it is said that it has an abstraction. So abstraction is basically, if you talk concretely, it is an unevaluated function, kind of an unevaluated function, but and there's an application which you can apply to lambda terms, and it starts the process of substitution. It substitutes the variables, all this stuff. I think I'm going
Mm-hmm.
too deep with it. Or so yeah. And what else? So yeah, as you mentioned, the it has so abstraction of x over x squared plus one gives all the stuff. So it's just basically it also shows that can be used as a function. It gives some examples of the function of absolute value. It also introduces the concept of beta reduction, which is basically substituting the apply argument to the variables, to the bound variables in M. So, so yeah, in this chapter is basically about the constructs and beta reduction.
Right,
So
right, right, right. I think that's correct. Right. So this is interesting. When I was reading this section, I had kind of a realization, revelation. Um, so basically, what I understand is that when you're talking about functions in general, you have to deal with two things. First, how you construct that function, and then how you evaluate that function, right? So it's like, if you, okay, you're like saying f of x equals to x squared. Okay, that's saying that we're constructing it from these x squaring, these numbers squaring themselves. But how are you going to evaluate it? Like, what is the method for evaluation? So there's this, two processes that are kind of interconnected with each other. um, so I'm just going to like basically say what Kai already said. Abstraction just means, as we talked about, you have an expression, and then you set some variables in the expression, and then you abstract over it, right? So it's like you want to create a function that, I don't know, uh, again, says x times y. It takes two variables and multiplies them together, right? So what we're doing is, okay, we take examples of how we can do this in numbers. We do 1 times 2, 3 times 4, and so on. And then we say, okay, we can just replace all of these numbers by x and y. So we created an abstraction of that. That's all that abstraction is, right? And it is denoted like this. X is an abstract thing in the expression M. So whenever you imagine something like M, imagine an equation. Something like an equation. It can be a differential equation, it can be not anything, but it's an equation. And this thing is the variable that is in that expression, right? So so that's an abstraction, and then application is basically how you um, take two expressions and construct a new one. So application is like the very like basic way of taking two things and creating a new thing from it, right? So like we took x and y, and then how do we create a new thing x y? Well, we multiply them, right? So this is basically a way of applying something to something else. Um, and once you have these construction principles, so for constructions you need these two. Once you have them, you can construct a function, but you cannot evaluate it. To evaluate it, you need beta reduction. We're going to talk about it later. Basically, you need to substitute the values, right? So if you have f of x equals to x squared, how do you evaluate this function at a particular point? Well, you put in the value of x in the expression. So whatever the value of x is, let's say 25. So 25 squared is going to be 625. So that's the evaluation. So you substitute the variable in the expression. Right. Now the interesting realization that I had is that when I was doing Lisp, right? Back when I was learning Lisp, the basic idea of Lisp is the eval function, and the eval function works with the apply function. So if you see here, it's the same thing. You have application and then you have evaluation. And abstraction is already implicit because we're defining variables. We're defining S expressions in Lisp, and they're already abstractions. So you have application and you have evaluation working in a loop, like the in-ang. I think I already have it in my Emacs here. Yeah. So you see this in-ang of common Lisp.
Yeah,
This is the eval and apply, and I think this is what we have in the lambda calculus here.
yeah, really nice analogy. And yeah,
So eval when we evaluate something, so we must substitute all values for the variables.
Yes.
And when you apply something to
Mm-hmm.
it, it's not necessary to be a concrete value. It can be an abstraction too, if I'm right.
Yes. Yes. So that's the thing. It's not like you can do application without evaluation. You need to evaluate to apply, and while applying, you're also evaluating, and
Yeah.
that's why it goes in circle.
yeah. Also, the one of the premise of the book is that it starts out by untyped lambda calculus. In untyped lambda calculus, some terms may not make sense. You can pass
Right.
not just concrete values, but another abstractions and so on and so forth. At some point, might not make sense, and then the book introduces the concept of simply tapped lambda calculus, so that the expressions will make sense. And
Right.
so on.
Yeah. So yeah, for now we don't worry about what makes sense or not because we are not like bringing in more semantics. But when we bring in more semantics with a type structure, um, we have to restrict things. Yeah. So yeah,
Also, this
I
chapter
think until now it's all good. No.
That's perfect. We need more abstraction, more comprehensive topics. So forth, it kind of feels obvious, but I
Mm-hmm.
think there is something is hidden that will appear later. Some
Yes.
concepts hidden in these applications and examples.
Yes. Well, yeah. I think the rest is just some. Yeah, this is an interesting thing. You cannot have lambda calculus denote multivariate functions, right? So if you have a
Yeah,
function like f of
very.
x y equals to x squared plus y squared, you cannot do that in lambda calculus. So you have to do currying. That's basically what currying was. And I think you also do it in Haskell in similar way, if I remember.
It is automatic occurring.
So in
Yeah,
lambda calculus, sorry,
mhm.
interrupt you.
No, go ahead, go
So
ahead,
in
go ahead.
lambda calculus, so we define these protections via guards, via function guarding. Yeah. If we have an,
Uh,
so we basically saying that x can be greater or equal to 0
mhm.
or negative x. Yeah, the function absolute value is definition x if x is greater or equal to 0 or x is less than. So can you explain this notation? Actually, I'm
Yeah,
struggling with
yeah,
that.
yeah,
What does
yeah. No,
actually
no.
mean?
So
Sorry.
yeah, so this point is basically saying that when you have like this case definition of a function, it's going to be difficult to describe it using lambda notation, right? And they don't do it now because you need an if then else. Because here, the absolute value function, what it does is it takes an x and it returns x if x is positive or equal to 0. Okay, so the function will return the same value if x is greater than or equal to 0, or it will return the negative value of the same number if it is less than 0, right? So I don't know if I can draw the graph of the function, if you want to imagine, is going to be something like
Shouldn't
this.
it be the reversed version if we're talking about absolute value? So either it doesn't matter to the sign, which sign it is. We always have the x without sign. So this notation says the notated as a reversed version.
No, 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 no. Uh, the idea behind the absolute value function um, is that it tries to what can you say? It gives you the non-negative value of x, right? Um, so just hear me out. So when x is negative, the absolute value is going to be is it's like, okay, I'm just confusing myself at this point. Um,
Basically, just can I try to explain it?
yeah, go ahead, go ahead.
Yeah, so it is not a lambda calculus at this point. So if you don't understand it, do not worry. Just a mathematical notation. Mathematical notation
Sorry.
sucks at most points. So basically, absolute value does is that the if x is already bigger than 0, it just returns the x itself. If x is a negative less than 0, then it is a negative.
Yeah, I
And if
know what
you
is
deviate
absolute
the deviation,
value, but I'm
yeah,
confused that this notation is confusing other people who's reading it because we
ah,
have an
the order
x
is
from
okay.
the left side and there is an arrow pointing to the right side, and inside the curly braces we have x if x is greater or equal to 0, or negative x when it is less than 0. I mean, it
Yeah,
is
yeah,
some kind of opposite notation,
yeah.
and it
It's no, no. It's
confuses.
not opposite. It's negative of negative x, right? So if x is -3, you're going to get minus of minus 3.
Ah,
You see, so that will
now
be
now now
plus.
now I get you. Yeah, thank you.
Yes,
Thank you very much.
yes. So if you don't put in the minus, you're going to get the negative number. You see?
Yeah, I get you. So they cancel out each other. So we left
Yes,
with x.
yes,
Yeah, great.
yes, yes. Okay, yeah, that's uh, that's that. Yeah, they don't give a like serious definition of beta reduction, that they will do that in 1.8. Here they just say that beta reduction is just substitution. That's basically it. So you have lambda xm applied to n. It's just m, the expression m, where x is substituted by n, right? That's what we have now. Until now, they will say more when we reach 1.8. One thing that they do say, and it was a bit difficult for me in the beginning, is that reduction happens on some parts of expressions. In the sense that, so if you have x square plus y square, you could just replace x and leave y. So that will be like partial reduction. You see? So you replace only the x's and not the y's. Um, yeah, and the whole set of rules according to which you can do reduction are the compatibility rules, which they don't talk
So
about.
can I
I
have
found this
a
part of
question? Sorry. Oh, can
yeah,
you move to the previous page, the end of the previous
sure,
page, and
sure.
we have the notation lambda x returns m, and we pass n, right?
I lost my network. Can you hear me?
Okay, can you hear me? Yeah.
Yeah, I can hear you.
So we
Yeah.
have the lambda x returns m and
Mm-hmm.
applies to n. So we skip the
No, no. This is not lambda x returns m. This is x as an abstraction over m.
uh-huh.
So
Lambda x
this
has
whole is a
huh?
function. Yes. So imagine this as f of x. So this is f of x equals to some expression where there is, some equation, x squared plus y squared or something. So this is that part, that expression, and this part is the what you're abstracting over. You see?
Okay. Can m
Yeah.
contain the x variable also? Because from
Yes,
this
m
point,
contains the
ah,
yes, m contains the x. That's why you can abstract over it.
okay, thank you. Uh-huh.
Yeah, you had some other question. I interrupted you, I guess.
No, that's fine. Thank you very much.
Okay.
It's clear
Okay.
for now.
Okay. Yeah, so this part is I was confused in this part as well, because like they speak in a very weird manner. They don't exactly lay down the compatibility rules, um, but they are like giving examples of it. So I was a bit confused. Um, but I understood this one because this is just like it's just the identity function. Um, like you have just x you're abstracting over, so like you're not like this function does not do anything, so you can just reduce it to this.
Can we say that the it is identity function passed applied to the identity function?
Yes, so it is so identity function of x applied to identity function of y.
Mm-hmm.
Yeah, theoretically they're the same, but here you have to act as if they're different. Yeah. And they also make it clear here that application is kind of difficult to talk about. because when you talk about application of M to N, you don't have the result of applying M to N. So it's like application is like an expression in itself. So think of application not as what the value you're getting, but more in the abstraction that you're creating. So application itself is an abstraction. Does that make sense?
Yes, yes,
Yeah,
yes,
yeah.
yes. So we reducing the expression, and it is an abstraction, not necessary to be a value. The
Yes,
result of application.
yes, yes,
It
yeah.
might be
So it's
other
like,
equation. Other
yeah, it's
equation.
like
Mhm. Sorry.
it's like applying f to g. So f of g of x, like concatenation f of g of x. You don't know what the result will be, but all you know is you're applying f to g. So that's what they're talking about in the application part, is that it's a construction of a new expression. You're constructing something new using two things, but you don't yet know what that thing will have the value of. So yeah.
Yeah, that makes sense.
Yeah, that's that. Then they have this remark about currying. Yeah, basically, if you have like two variables x squared plus y, you can just say you have abstractions x, y. You have to say that first you abstract over y, and then you abstract over x.
Mm-hmm.
Yeah, this is a bit subtle, but that's how you need to represent these multivariables.
Is it shortening allowed? So we can write as a lambda xy, and then. Sorry, can you repeat the lambda x implies the expression x plus 1? Or how can I read or speak?
So, so, so if you want to shorten, there's a remark down the road. Uh, so, you can shorten it, but actually it is still going to be curated. Like you can, if you are going to chat, so you can shorten it like, let's say lambda x, lambda y is just x to y. You can shorten it like x y and x y. Like,
Mm-hmm.
but it is explained later in the book.
Okay, fine, perfect.
Am I right? Like, are you here?
Okay, am I audible?
Yeah,
Yeah, yeah, yeah. You are.
Yeah, uh, my luck is terrible.
it's okay, it's fine.
uh, no, so I was just wanting to give an example in Haskell for currying. So um, so this is like the non-curried version of addition function in Haskell, right? So you say that you're taking a pair of integers and you're giving an integer, right? So you have add xy, you get x plus y. That's the non-curry definition. But the curry definition is that, okay, so you have add prime, and what it does is it takes an integer, but it gives a function which takes an integer to an integer. And that's the magic here, is that if you look at here, is that after lambda x, you don't have an expression like m or n or anything. This itself is a function. So in currying, you take functions as arguments, right? So you have int that gives a function which in itself takes int and gives int. That it might take a bit of getting used to, but so what it does. So if you look at this one, I no longer have to write add x comma y. I just write add prime x y. So what this does is that first it creates a new function. So this one you see add prime x. This is a function itself.
Mm-hmm.
I, I might add like parentheses here. Might be um, so this in parentheses. This is a function, okay? And what is this? This is just the result of taking an integer and giving this.
Mm-hmm.
You see, so this thing, like this type signature, leads to this function. Okay, and now what does this function do? This new function, well, this new function, as we write in the type signature, it takes an integer and gives an integer. So this function takes y and it gives x plus y.
Mm-hmm.
So you see, so you do not like immediately calculate by evaluating. You take something, you create a new function, and that function gives you the value. That's the goal of currying. Um, does that make sense or not?
Yeah, that makes, but when we evaluate this carried function, where do we
Mm-hmm.
start? From the end? From which side of onion we start? From the outer side
Okay.
or from the inside?
Yeah. So you start as the type signature said, from what this is. So this is the integer. So again, okay, let me do this. Okay, so this outer thing is the main function,
Mm-hmm.
right? So that function takes integers and creates a new function.
Mm-hmm.
And then that new function evaluates something, right? You could do the other way also. That the other way also works, and that's why it is recursive, right? Um, but to understand, it makes sense that you start from here. Otherwise, you can start from either way because again, as I said, it's recursive.
Mm-hmm. Yeah.
Yeah, I think I also had another example. This one is a bit difficult. It is like 3 levels. So it
Mm-hmm.
takes an integer, then creates another function, and this function gives another function, and finally you have this. Um,
Mm-hmm.
so yeah, and again, it's the same in Haskell. In Haskell, when you're working with tuples, which is what the book said, right, with multivariable functions, um, you can partially apply a create function and be just done with it,
Mm-hmm.
right? So like I can just do add prime x, and it will be fine. I don't have to worry about what's next, right? So yeah, and this is just the like logical version of what we saw there.
Mm-hmm.
Um,
So as the Inyan you said
mhm,
before, it has
mhm.
uh, the evaluated value and at the same time the expression, so you can chain them back and
Yes,
forth.
yes, 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 yes. So what you evaluate this, then later dictates what you will evaluate the whole thing, right? And
Mm-hmm.
then what, as you evaluate the whole thing, that will also dictate what this becomes, right? So
Mm-hmm.
this is very interesting, like because like to me when I see this, it feels elegant. It's like you you have so much complexity in functions, and then you have this one line way of describing things, and it's difficult one immediately to get it, but once you get it, it's just beautiful.
Yeah, did you heard about closures?
Yes.
In yeah, it is have the same thing. So you evaluate the first layer and then reuse the value from the first layer without redeclaring it every time.
Right. So there's like this lexically scoped binding, right?
Yes,
There
yes,
should
yes,
be
yes.
some lexical. Yes.
Uh-huh.
Yes. So lexical scoping allows you to do that. Yes. But yeah, that's the thing. So that has the foundations in this. We will see later on. You cannot actually implement lexical scoping, or like you know. I think you're familiar with free variables, right? In programming, the free variables of a function.
Free variables which are not used in the expression. You
Yes,
mean this
yes,
thing? Uh-huh.
yes, yes, yes. So that is going to be from this. Um, so, so yeah.
Uh, you may
So
have the outer layer, but you may also not use the value,
exactly.
yeah, variable from the outer layer. So we have the free
Yes,
variable. And
yes.
actually, the page before when we saw the x, can you please repeat how to
Mm-hmm.
pronounce this expression? Lambda x, and then it implies or what?
No, you can just say lambda x dot m. Like you can just read it as lambda x dot m. But what it means is x is an abstraction over m.
Ah, okay. So
Yes.
shall we prepend the lambda word? Lambda x is abstraction over m?
No, lambda just means lambda is the shorthand for abstraction.
Ah,
Lambda
okay.
is what makes x the abstraction, right? So x is the abstraction. Lambda x just it's like denoting something that this thing is the abstracting one.
So is the this statement correct in the chat?
Oh, let me see. Yes, 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 yes.
Dot m? Uh-huh. Okay, thank you. And when we evaluate, so we bring the n,
Mm-hmm.
we say x is an abstraction over m, and it applies n. Yes, x the x dot m. So we can put it like this. Applies n. Sure.
Yes, yes. So what you wrote can be written like this. So it's going to be just lambda x dot um, mn, or just brackets mn, right? So that m implies n is just mn.
Implies or applies?
Applies, applies.
Applies. Okay. It is the dot from the category theory. Yes.
Yes.
Okay. Thank you very much. Abstraction over M.
Yeah, yeah. So so yeah, I think so. Like if you look at this, right? So mm, so you have g equals to lambda x dot lambda y dot x squared plus y, right? You're looking at this expression, right?
Yeah.
Um, so here we were saying that x is an abstraction over this, right?
Mm-hmm.
But here we don't know what this is, because already here we have y as an abstraction, right?
Mm-hmm.
So first you need to figure out what this evaluates to, then substitute x for that, right? So this is what they do. So if you have um, two variables, you will just put in the first one and then the second one, right?
Uh-huh.
So first you do 3. So g of 3.
So
So
x is
g of
3.
3, yes. So x is going to be 3. So it's going to be lambda y dot 3 square plus y,
Uh-huh.
right?
Right.
Now, lambda y dot 3 square plus y is itself an abstraction, itself a function. You
Uh-huh.
apply that to 5. And then what happens is you have 3 square plus y substituted by 5, which is this 3 square plus 5. Right.
One question here. Can we write
Yeah.
is like this way without giving the one more parentheses?
Yeah, yeah, you can do that. They just do that just so that it makes sense
Ah,
for
okay.
people. Yeah. Yeah. But the idea is that g of 3 itself is acting upon 5. Yeah.
Yeah, it's easier to imagine that again the onion example. So you start unlayering
Yes.
the onion. The first argument you pass, you unwrap the top layer, and then you go up to the bottom or up to the center.
Yes.
Yeah.
So this is the way we deal with two or more variables uh, in lambda calculus notation.
Mm-hmm.
Okay, yeah, I think we are doing good progress on this.
Uh-huh. So can we call the beta reduction uh,
Hmm.
as an application? The application, the expression over the value. So beta reduction is
But
basically the parentheses. So
mhm.
um, like this thing. It is
Right,
called beta
right,
reduction. Yeah, am I right?
right. But the thing is, 3 is like a value, not an expression.
Uh-huh.
Um, so just to make definitions consistent, application is when you're applying one expression to another,
Ah,
and evaluation is when you are applying for some value. So G applies 3 is an evaluation because it is generating some value. This is producing, yeah. So it's creating a value. Um,
um, okay, I gotcha. So uh we say apply when say apply for only expressions, not values. Uh-huh.
yes.
Okay, thank you.
Yeah. Yeah. When values come in, you're evaluating.
Yeah. Earlier in the book, it was also said that we can imagine the lambda terms as a tree. We build up the tree. Application is also wrapping, continuing wrap the onion further and further and further, and better reduction, and we better reduce. Then we start the process of kind of a calculation or the
Right.
evaluation.
Right. 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 Yeah. Yeah. This is the thing. Like I think because like they're trying to be like they don't want to like scare the reader away, so they don't introduce beta reduction yet. Uh, they keep it for later. So yeah.
Mhm.
Yeah. Okay. So the next section is some lambda terms. Um, Now, lambda terms is basically everything that you see already. So, like everything that you see with lambdas, these are all lambda terms. It's basically what you're operating on. Um, Um, so variables, applications, MN, abstractions with lambda, everything is a lambda term, right?
Basically, the syntax of everything we've done, it
Yes,
is lambda term.
yes, yes. So they're going to actually do a recursive definition of lambda term. Um, sorry, inductive definition, not recursive. Yeah, yeah. So basically, if you see the screen,
Yeah.
lambda terms can be of three kinds, right? So they are either variables, applications, or abstractions, right? So the set of all lambda terms is basically all of these things, right? If your term or if your expression is a variable, then it's a lambda term. If you have two lambda terms, then their application is also a lambda term.
Mm-hmm.
And if you have a variable and a lambda term, then the abstraction of the variable over the lambda term is also a lambda term.
Mm-hmm. Mm-hmm. Yeah, it's more clear now.
Yes. Yes. So you see, you build from small. You build from variables, and then you uh, go to applications, and then go to abstractions.
Mm-hmm.
Yes. So basically, anything that is a lambda term can be defined according to these three definitions.
Yeah, there is a shorter version below. Yeah,
Yeah.
either variable, either application of the expressions, or
Yes.
um,
Abstraction.
abstraction of variable
Yes.
over expression.
Yes. Yes. Yeah. That's it. That's the lambda terms. They have some examples here. Um, yeah.
Mm-hmm.
So these are all applications. These are all abstractions. Um, so here it's like abstraction as final step, meaning that the final result is an abstraction.
Mm-hmm.
And here application as the final step means that the final result is actually something like this. Um, yeah, why don't you read one of these, because it might not be immediately clear why this is.
So it is something. Um, how can I say? It is something from mathematical simplification. When
Mm-hmm.
in the end you have a compact form of
Mm-hmm.
algebraic expression,
Right.
but the first form of it was not that compact. It was
Yes. Yes.
comprehensive, and also that means the behind the abstraction we have the infinite different kinds of expressions. So we have
Mm-hmm.
infinite amount of plus ones or something else, if I'm describing it well. Abstraction
Yeah.
is
No. Yeah.
nah. Uh-huh.
Yeah.
Uh,
So basically, when you're seeing, so like, look at this thing. So this has this big parentheses, which has these two things, right? So there's this and there's this. So um, so what you're trying to do here is that in each of these parentheses, you have one thing applying to another thing.
uh-huh.
You see, but here this was not the case. If you look at this one, Here it was just lambda x dot some expression. Here it is the lambda x, or the abstraction, is included itself in a parenthesis, which means that abstraction is going to be applied into something, right?
Mm-hmm.
So that's why it's the final step is the application, because the abstraction itself is getting applied.
Mm-hmm.
Yeah, that's pretty much it. It's I think like if you do it on pen and paper, or maybe some writing, you'll get used to it. It's just
Yeah.
notation.
So far, so far clear. Yeah. Thank you very much.
Yeah. Yeah, then, well, if you have two expressions or two lambda terms that are exactly identical, syntactically identical, um, then you just write it as this equivalent. So this is equivalent
That means
or identical.
synthetically, but what about semantically? If they
There is no
both
semantics.
ah
There is no semantics. That's the thing. It's like, if they can be reduced to something similar, then they're same,
uh-huh. Okay.
right? So if
So
if
we are
their
taking
compact
the
forms are,
simplified, very
yes,
simplified form
yes,
and compare them. Okay.
yes,
Thank you.
yes, yeah. And then we have the multi-set. This one is a bit confusing. Well, Kai, why don't you tell us a bit? I've been speaking for too long.
All right. So multi-set of subterms is basically uh, when I implement it made sense when I implemented it actually. So um, basically subset of a variable. So it has an inductive definition. Basically, a subset of variable is a variable itself. So multi-set. I didn't have any idea what multi-set was, so I used a list with my implementation. So the multi-set of subterms is basically the list of each subterm, list of each terms. So we just take the, as I mentioned before, we take the each element of a tree and just put it in a list. So if we look at the definition, so the basis, subterm of a x, subterm of just a variable is just the singleton of a list, just a list with the one element. After we, apply it recursively, there are, as you can see, union symbols. The lists get concatenated and so on and so forth. Basically, we just return a singleton list. I, I I'm I'm telling list because I don't have any idea what multi-set is. So what I found on the internet was that it's just basically like a list where in a set elements cannot be repeated, but um, so basically the application of a so the subterm of an application is the union of the m of the expression of the subterms in the expression m and the union of the in the subterm of the expression n and the union of the application. We just put the expression itself too. So basically, what we're doing is we're collecting each and every term into a list. So what happening in the second case is we just put the expression itself, and then we continue recursively collecting subterms, each and every subterm. And in an abstraction, we just put the term also in a list and then union with the subterms of the m. So the result is going to be if we have, I don't know, I can share my screen and show some results.
Sure, sure, sure.
So let me open up VS Code before that. So write TFP. So Can you all see the screen?
Mm-hmm.
Yep.
So don't mind the alphabetic loans. I cannot prove termination for it. So just let's comment it out. So basically, here's my definition. So here's my definition of the lambda term. It has a variable which has a name, which is a string,
Mm-hmm.
application abstraction. Simple enough. So we're just going to ignore it. And here's the definition of a subterm. So as we can see by the definition in the book, the subterm of a variable is just a singleton list, a list with one element. As we, continue traversing the lambda term, we're going to collect each and every subterm and then concatenate it, and then build up the list. So it may not be clear, but it, it's going to be enough if you get the main idea. So if it is an application, so we just take the term itself, append it to the list, to the head of the list, and then continue collecting the subterms in M and N. So the T here is, we can just substitute it to, F, M, N2. So it's going to work abstraction of, can just do it. So we're just collecting the term itself, and then we're just recursively uh, collecting the subterms. So the result is going to be, so as you can see here, uh, so the let's say we have an example, so we can just evaluate the example. We have the following. So the abstraction, which binds the variable m over the expression, over the application of variable x to the variable y. So basically, this is our example. And if we take the subterms of the x of the example, as we can see that the first element. So let's start from the last example, from the last element. So as we can see, we have the subterms here are, we can say that y is a subterm, so is var x, and so is the application of var x to the var y, and then so is the abstraction of x to the application. So yeah, this is the multi set of subterms. As you can see by the example here, we can just turn it to string. It's basically y, and then x, an application of x to y, and then the abstraction that binds the x to the x applied y. So we're collecting, as you can see. Let me share the book. So as you can see, uh, here it is given the tree. We can imagine the lambda terms. Lambda term is a tree. We're just going to collect this, and also this separately, this as well. So we're just going, traversing the tree and collecting the results, collecting each term. So, any questions?
I didn't get the second uh, where application where we have a
Mm,
subterm of n applies to which equal to subterm m union subterm n and union the last thing I didn't get it mn
yeah. So,
in parentheses.
no, no. Divya left or
Yep. Yep.
yeah.
Yep.
So,
I'm here.
all right.
Yeah. I
So,
I can try to explain that
Mm-hmm.
if
mhm,
you want.
Yeah,
Yeah.
please.
So yeah. So basically, let me get my scratch pad. Right. So basically, the idea is that when you're doing some expression, some application, right? So some application means you have like let's say x applied to z or z, right? So what this means is that this thing is what you're trying to find subterms for, right? Okay, so the rule says that what you do is you first find the subterms of the first thing that you're applying.
Mm-hmm.
So the first thing is x, and then you take the union. I'm just going to represent union with plus. Um, so sub x union the subterms of y, okay,
Okay.
sorry, z, because the second thing is a z.
Uh-huh.
So if you take the subterms of the first thing, you take the subterms of the second thing, you union them, and then you union the subterms of the whole thing itself.
Ah, it just means the first thing. It's like a
It's
uh,
a recursion, basically, right?
ah,
So basically, what it ensures is that what you're taking the subterms of, it is itself included in the set.
ah. Now I get it. Yeah, thank you very much.
Yes.
So the least significant, I can say, thing is the basis or the variable.
Yes. So least significant in the sense that it is trivial.
Yeah,
So like if okay, if we try to go further this thing,
yeah, it's
um
primitive. The in other words.
yes.
Mm-hmm.
So it's going to be the set containing x because subterms of x is just x, subterms of z is just z. So
Mm-hmm.
it's going to be x, z, and xz.
Mm-hmm.
That's the set of all subterms for this. Make sense?
Mm-hmm. Yeah.
Yeah. And that's what the tree does as well. The tree has some notation to it. Um, but if you just look at this part of the tree, this leaf, so you have this as an application, and this application is just what we wrote. It's this one,
That's it. Uh-huh.
x applied to z. So
Explain to me.
what this leads to is just x z. So you see, subterms of xz is the application itself, xz, x, and z.
Mm-hmm.
These three things are the subterms. You see?
Yes. Does
Yeah.
the input x, lambda x, counts as a subterm itself, by itself?
Yeah, right. So that's the third definition, right? So that's for the abstraction. So for the abstraction, what the definition says is that, okay, so you have subterms of this abstraction where x is an abstraction over m. What you do is you first take the subterms of the expression m, okay, we do that,
Uh-huh.
and then you union it with the single
Itself.
set. So again, this is a single set of itself.
Okay, what about free variables?
We're going to do that very soon. We're going to do that very
Ah,
soon.
okay, okay.
uh yeah, it's like the just the second next section.
Mm-hmm.
um but here already you can see like we're taking very simple examples. We don't have like y outside here. We don't have anything outside in the outside layer,
Mm-hmm.
right? If we had anything in the outside layer, um, you have to take subterms of that as well. You have to
Mm-hmm.
union that,
Mm-hmm.
right? So yeah. So just to see, this is what the tree looks like um, for this. Um, and what the tree is basically, um, okay. If you look at this expression, you have what? You have y applied to this abstraction,
Mm-hmm.
right?
Right.
Okay, right. So you start with the first thing as A because you have application. We write A for application. So because we have the first thing as application, we're okay. We say it's application. What is it an application of? Okay, it's an application of y over some lambda,
Mm-hmm.
right? So we have application of y. Then the second thing is lambda x, right? So lambda x denotes abstraction. Okay, so this leaf in the tree denotes abstraction.
Mm-hmm.
Well, what is it an abstraction of? We look at here. What is it an abstraction of? It's an abstraction of an application,
Mm-hmm.
right? So lambda x is an abstraction of some application that is A, and what is that application? Well, that application is just xz.
Mm-hmm.
So that's how you traverse the tree. That's how the tree works, right?
Mm-hmm.
So if someone asks you, like, what's the subterm of this whole thing? Well, you just say, okay, this is this application y, this lambda
Which is
application xz.
application. Yeah. Mm-hmm.
Yes.
Yeah, it's more clear
Yeah.
to think about it
Yeah.
in terms of
Yeah.
this tree.
Yeah. 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 Like, believe me, like, there is nothing in it but just following the notation and brackets. That's pretty much to it.
Yeah, but it's too much abstract, and getting into this takes some time. And after
Yeah.
the progress, you realize that it's nothing.
It's nothing.
Yeah.
It's nothing. Yeah. Yeah. I have to tell you, in my years of mathematics, this is the only thing constant. Yeah. Yeah. Well, after that, they just define something. Proper subterm just means, um, you know, L is a subterm of M, but it must not be equal to M. Just like subset, A is a subset of B, but A must not be equal to B, right? Because then it's just trivial. Yeah, I was thinking, Kai, did you do the proof for these two, reflexivity and transitivity?
So I proved the let me look. So I proved the reflexivity, but I actually proved the transitivity too, but using a library called, I don't know how to pronounce Aesop. It's written as following. I have the proof, but
ESOP. Okay.
no, it's not. Yeah. So basically, it was nothing. I just use simplification, so
Yeah,
simple,
okay.
all simple, simple everywhere. Yeah.
Well, as
But
an exercise, why don't we take some time and try to think about these two? Um, yeah,
uh,
like how to go about proving them, like mathematically, let's say.
I don't know anything about
You
mathematical
don't have
proof.
to know
But
anything. You don't. Just think about how you can, like, say that this statement is true. Like, use
so,
these definition and, like, just what you can use to make this true.
I think the exercise is going to be easy because we have an inductive definition. So
Mm-hmm.
reflexivity is pretty easy. You can just um, I don't know, reduce, or what do you call it? So if we just match case by case, if we have a variable
Right.
and on the left hand side, and we have a variable on the right hand side, and the names are equal, so it is reflexive. So and we just match case by case and can just continue evaluating. So if we don't have, if you have, for example, have the variable on the left hand side and and abstraction on the right hand side, then it is not the same.
Right.
But I don't know the proper terminology for this, so I'm just
Mm-hmm.
so basically we just match case by case and then just simplify it. Like the, for example, we just according to the definition, we just match m, and if the m is a variable, then um, so
The subterm is just going to be itself. Yeah.
yeah, exactly. I think it's going to be itself. And if that's an application, subterm has to contain the application itself and
Yep.
the so we can just apply proof recursively.
Yep.
Yeah, that's so. We just we prove this by using the aforementioned definitions and
Yep.
the how do I put it, the properties of the multiset, or in my case, properties of the list. So
Yep. Yep. Yeah, that's pretty much it. You just go case by case.
yeah,
Yeah. I think obviously it's clear also to you um, that basically in every definition the expression itself is included in the subterm.
yes.
So so it's trivial that for all lambda terms the expression must itself be a subterm. So the reflexivity is given for that. What about transitivity? Should we try to do that?
So transitivity really made me pull out some hairs from my head. It was really so. What I did initially was
Mm-hmm.
uh, it is actually not that hard. It turns out that it's not actually that hard. We just match inductively, case by case. For example, I matched on the so we have L and N. So L is a subterm. If the L is a subterm of M and M is a subterm of N, then L is a subterm. L is also subterm of N. So what we can do is just use the aforementioned inductive definition and match case by case on N. So I start matching on N and just simplify everything off. So in the first case, if the N if the N is a variable, we just um, prove it like we did prove the reflexivity. How do I put it? I don't know. Like so, in the case of a variable, so we just I don't know how to put it, but
Mm-hmm.
so most of the things. So I proved the var case and abstraction case by myself. So using simple and the simplification of the definitions of the sub and subterm.
Mm-hmm.
And the application part was really hard, and that's where I used Hazel.
Okay. Okay. Yeah.
Because automatic proof search and introduce and all, there's a lot of stuff.
Yeah. Let me see if I can
Can we
try to
say
describe.
that
Mm-hmm.
L is abstraction over M when L contains in subterm of M?
L is an abstraction of M if L contains any subterm of M.
Yes, something like this. I'm not. I've not done any proofing before,
Mm-hmm.
so I don't have a knowledge about inductive methods. But logically speaking, we first proved that the M, which one? The reflexivity for all lambda terms
Mm-hmm.
M, we have M, which contains in subterm M. Yep.
Yep. Yep. Why don't we do this more concretely? Okay. So can you see my screen?
Yeah.
Yeah. So let's say we have M as XY. This
Mm-hmm.
is an application. N as, let's say, I don't know, AB, and L as PQ. Okay, so what do we need to prove? We need to prove that L in sub of M
Mm-hmm.
and M in sub of N implies that L is in sub of N.
Mm-hmm.
Like that's what we need to show. That if something is in one thing and that thing is in another thing, then that one thing is also in that another thing.
Yes. Mm-hmm.
Right. So how do we go? Is okay. So we say that let's take L. Right. So L is PQ. Right.
Mm-hmm.
So PQ is in the subterm set of all subterms of M. So what is the set of all subterms of M? That is
X
just
and
X,
Y.
Y.
Mm-hmm.
So it's going to be X, Y, X, Y,
Mm-hmm.
right? So we claim that PQ is in there. Okay. Again, maybe it's just equivalent to something, we don't know. We just say that it's there.
Mm-hmm.
Um, then we say that M is also in the subterms of N. Okay, so what is M? Well, M is just XY. XY is in the subterms of N, which is just this A, B, A, B. Right.
Mm-hmm.
Okay, so now um, if we try to, figure this out, so this is just uh, X union Y union XY. Right. Now, the idea is that the subsets, sub terms of n is also going to be just unions, right? So this is going to be unions of A, unions of B, unions of AB.
Mm-hmm.
Now, if something is in here and then this whole thing is in here,
Yes.
then what we claimed to be in here must also be in here,
Right.
because we just said that this whole thing is included in this,
Mm-hmm.
and in that thing is this.
Mm-hmm.
Does that make sense? So if PQ is something that in here is going to be either equal to X, either equal to Y, or equal to this. No other possibility exists, right?
Right.
And
Huh?
then we say that M itself, that is XY, is included in here, right? So if XY is included in here, and here is just what? AB, AB, then what we claimed to be here must also be here.
Mm-hmm.
Does that make sense?
That makes sense. And it is foolproof?
No, the this is the like the spirit of the proof. If you have to do the proof, you have to actually write an injective function. You have to write a function that takes an element from this to this, and then you have to prove that this function is
With
uh,
triple equals,
all
right? That
yes,
they are syntax.
yes, yes, yes.
Mm-hmm.
So that's the, but again, the idea of the proof is that you cannot claim that L is a sub is in the subterm of N, because in the subterms of N you already have a singleton, and this one. So L has to be equivalent to one of these, right? So
Mm-hmm.
yeah, that's more or less the idea. But if you do the abstract, so this is for the application, right? So for the abstraction part, it's a bit more complicated, because you will have lambdas. But I would recommend, try to like write down a step by step algorithm for what you can do. I know, take something from L, then something from sub N, and compare them and see if you can have that. Yeah, proofs. Proofs are not easy.
Yeah, but they're mm, they're very interesting.
They're interesting. So that is, so again, a proof is just an algorithm generalized, right? It's like an algorithm that works every time,
Mm-hmm.
exactly the way it's supposed to. So you first write down the algorithm, and then you see if you can generalize it in some way, and that's it. That's literally it.
Yeah.
But yeah, maybe. So I'm in the process of writing down some notes. Maybe I will try to write down some, actual proof of this and share it in the chat, and then we can discuss. But I guess you already get the idea behind this.
Uh, Kinda, but I'm still struggling how to actually represent, as you said, the abstraction of PQ over
Uh huh.
XY and the abstraction XY over AB. Yeah, I'm thinking about it.
Yeah, it's like just think of it in these terms, right? It's like maybe, okay, maybe let's do the abstraction proof. Maybe that will shed light on this.
Mm-hmm.
So this time m is going to be some lambda x. I don't know. We'll do the same thing, I guess. Xy. N will be lambda a b, and L will be lambda p pq. Right. So these are all abstractions over some application.
Mm-hmm.
Right. Um, Now the point is, okay, we say that L is a subterm of um, n. So we first calculate the subterms of n. What will be the subterm of n? Well, it's an abstraction, remember? So when an abstraction, first we do is first we figure out the subterms of the expression that is an abstraction of. So
Mm-hmm.
we take the subterms of AB, right?
Mm-hmm.
Double parentheses. Then we union that with the abstraction itself.
Mm-hmm.
Right? That's the subterms of n. Correct. We can simplify this further because this is an application. So subterms of AB is just going to be A, B,
NIB. Uh-huh.
AB. And we can just, do this here, that the next thing will be is just an abstraction itself. Okay, so it's the
Mm-hmm.
same thing. We
Mm-hmm.
put the same thing back. Okay, so this is a set of all subterms of n. Okay, so then we claim that, okay, L is a subterm of n, then it has to be either of these, right? It has to be
Mm-hmm.
some of these. It cannot be anything else. Yeah.
But first,
Um,
should we make subterms of M? Because,
yes.
uh-huh.
Yes.
So the point is,
So,
L is inside of M, and M is inside of N.
ah, okay, okay, okay. Yeah, that's a mistake. It was M. I forgot.
Mm-hmm.
Well, then we should first write down the subterms of everything, I guess. Um, I guess you can already see the
Yeah,
pattern here, you
yeah,
know.
better.
The subterms of, yeah, it's going to be x,
X, Y, X,
y,
Y.
x, y, lambda x dot x, y,
Mm-hmm.
right? Similarly, subterms of L will
Is
be just P, Q,
PQ.
P, Q, right.
Hmm?
Okay. So the idea is that if L, which is PQ, is a subset of, is a subterm of this, right?
Mm-hmm.
It's in this. So imagine this, okay? So if, you know, if you have one of these as a subterm um, of PQ, so it's like, let's say, forget XY. So we say XY is equivalent to PQ, okay?
Mm-hmm.
If XY is equivalent to PQ, um, and then we say that M is a subterm of N. Okay, so what is M? M is just XY. So XY is going to be here in sub N. Okay, then now we say that, okay, let's XY be equivalent to, what did I do it?
AB.
No,
AB.
no, no, just a second.
Uh-huh.
L is in sub M, L is PQ, XY. So it's the other way. It's supposed to be this way. So this is this, right?
Mm-hmm.
So if XY is equivalent to PQ and XY is also equivalent to AB, then PQ is also equivalent to AB. You see, XY is equivalent to PQ
Mm-hmm.
and XY is also equivalent to AB, right? So if A is equal to B and B is equal to C, A is equal to C.
So if we simplify the whole proof,
Yes.
so we can speak like, wait a minute. So we wrote x if xy equal pq, xy in our case is m, pq is l. So xy equal ab, where so we can write pq again.
Yes. So basically, what you're going to do is that if you claim that L is a subterm of M, or anything is a subterm of anything, you just look at all these things in that set and you say, okay, this has to be equal to one of these, right?
Mm-hmm.
And if it is equal to any of these, you can argue that, okay, it's equal to this, and that thing is equal to another thing, and then it has to be in there as well.
Mm-hmm.
So we took XY equivalent PQ. You could have taken XY equivalent to lambda x XY, right? Because again, these are just abstractions, you know, these are just symbols. These are not numbers, these are not evaluated. Maybe this is exactly the same as this, you don't know.
Yeah.
right? Um, so even if xy was equivalent to this, well, then we could have just said xy is equivalent to, lambda a b.
Mm-hmm.
You see, so then lambda xy would have been equal to lambda ppq, and then we'll say, okay, if L is an M is an N, then L is also N, the other one. So this is the argument. This is exactly the proof. You just have to write it in, you know,
Uh,
juicy words. Otherwise, this is the whole proof.
uh, can we just write down three statements with three triple equals? Because we defined the triple equals that mean in definition, which one it was? Triple equals. Notation 1.3.4. Yeah. We defined representation,
1.3.4.
synthetical
Yeah,
identity.
yeah, yeah,
We just proved
yeah.
the reflexive. No. We proved
Transitivity.
transitivity with
Transitive.
synthetical identity. Mhm.
Yes. Yes.
Hmm. Hmm. Mhm. Yeah, that makes sense. We
So basically,
used.
the goal
Mhm.
is that if you claim that you have this thing where L is a subterm of one expression, and that expression is a subterm of another expression,
Mhm.
then L is syntactically identical to one of the sub expressions of the last thing.
Mhm. So
So yeah,
can we switch to the book, please? We have
sure, sure.
definition 1.3.5,
Yep,
which helps us to split up the
yep,
row term to subterms. And we proved
yep.
with notation 1.3.4, which means synthetical identity. Okay. We used two of
Yes.
these definition and notation and proved. Okay. I was looking to learn some to do self-study in basic mathematical proving. I
Mm-hmm.
saw one YouTube video. He recommended a bunch of books regarding
Mm-hmm.
mathematics and how in which order to learn.
Mm-hmm.
So when basically I started to watch category theory videos, and at this
Mm-hmm.
some point I realized that it is way too abstract, so I need to uh, learn a bit basic things.
Yeah.
And he said that we can learn proving much earlier, so like the first or the second book after or
Mm-hmm.
in parallel of pre-algebra, he said.
Yeah,
Remember
yeah,
mistake.
yeah,
Mm-hmm.
yeah. Like I, I started doing serious proofs when I was in like eighth grade because I was doing Olympiad mathematics, and in Olympiad mathematics you have like proving. So proofs do not require higher mathematics. Proofs are just again just arguments for truth statements, whether something is true or not. Right. So
Yeah, I regret
yeah.
one thing when I
Mm-hmm.
skipped one lesson of mathematics in the school. It was not
Uh-huh.
mathematics, it was algebra. And starting
Ah,
from this lesson, everything is ruined. So I
right.
stopped learning um, uh, freeze at the school math at that point. Yeah.
Mm-hmm. Yeah, no worries. I think you'll get used to it. I think programmers already think in that kind of way, algorithmically. You just
Yeah.
need to be a bit more general in that thought. That's it.
Yeah, basically it is basically everything is clear, but um, only struggle is with notation and a
Yes.
bit of abstraction because we always tend to think in terms of uh, evaluating, but not
Yep.
applying.
Yep.
Yeah, I struggle with notation too. Like that's why even if my teacher at school showed me some proofs, it never made sense to me proving in paper. That's why I even picked up lean. Just proving something on paper, just I don't know, it just doesn't make sense to me. I can't understand it.
I'm afraid that I will make mistake in my proof and
Yeah, yeah, exactly.
no one can point you to your mistakes. So you will think that you're right when in reality you're not. That's the
There was a
biggest scare.
there was a group about type theory where there was Alex Grizlov, and he said that the proof doesn't have a value if it is not proved in a formal language. And he added that don't tell this to
Yep.
mathematics because they get mad. Yeah,
Yep. The thing is, whenever I teach, there's two calculus classes. Like one calculus class is like a computational, you like solve integrals. The other one is like more like real analysis influence approach, and so it's like it starts from proofs. And every time like I have like taught some people, they can do the calculus part, they can do like the computation, but when they sit down with blank paper, they don't know what to write. um, so like especially like what I do is like I don't emphasize so much on language. I think language you can learn with time. It's the same thing as programming, you know. You can get used to syntax. Syntax is not that difficult to getting used to, but if you don't know what the semantics are, you're not really going to make much sense. So it's the same way in the proof. Write down the algorithm, or like write down what you know is the computation, how to do this, and then figure out the language of how to do it. And you know it will be difficult a bit, but you will at least not be left with a blank page. That's what I'm saying.
yeah, yeah.
So,
You also have to, I don't know, be able to use correct properties, like assume
yes,
some properties that are true.
yes. Well, yeah. So I think we have already gone through much of this. They
Yeah.
just say that, you know, we are tired of parentheses. We're not going to use parentheses anymore.
Hmm.
We'll
Yeah,
just write MNL.
MNL, yeah.
Yeah, now we come to free and bound variables. So this is, I think, where the programming part comes in. Just a second, I'll drink some water.
Me too.
Okay, so I think in terms of free and bound variables, this is what I understand is that the variable on the outermost is going to be free. Again, outermost is irrespective to the onion layer you're in or the tree you're in.
Mm-hmm.
So here, it y is free. So because it is in the outermost. So this is the free variable, and this one is the bounding variable. So this binds stuff.
Mm-hmm.
So because we have lambda, so every time you have a lambda, you create a binding variable. And what this does is it binds every occurrence of x inside this lambda expression or lambda term. So inside this domain, right? So we have x as binding, and the expression here, every time you see an x, it is bound with respect to this entire expression.
Mm-hmm.
So x is bound here, but if you close your eyes to this expression and you just look into this one, this little application, here x is free because x is the most outermost.
Mm-hmm. Mm-hmm.
You see in the application x is free, but if you look in the context of this lambda term, this abstraction x is bound because you have this.
Uh,
Yeah.
free is in context in which you are looking
Yes.
to the term or expression
Yes.
in term.
Yes. Same way. So it's basically scope, right? We need to
Yeah.
look at the scope. Yeah. Yeah. That's pretty much it. I think. Uh, there are two variables. Sorry, there are two conditions. Where was this? No, sorry. So you can have the set of all the free variables of a lambda term e- using this recursive definition. Um, it just says that the free variable of just a variable is going to be the variable itself. The free variable of an application will be the free variable of first expression union free variable of second expression. You know? And free variable of the abstraction will be the free variable of expression modulo x, modulo the binding variable.
Mm-hmm.
So what this means is that so for example, let's see, if let me add another. So if you try to look for all the free variables of you know y applied to lambda x xz, I'm just ignoring parentheses now. um, so here you have to first, okay, so this is the free variable. Okay, we first do this free variable of y, and then we do the free variable of the rest of the abstraction,
Mm-hmm.
right?
Right.
A free variable of y is just the singleton y. Okay, so this is simple. Well, what about this? Well, first what we do is, remember, free variable of the expression xz modulo x. So what this will be is, this is uh, sorry, yeah, this is modulo x. Um, so union this will be just y x z modulo x. Modulo x just means remove all the x's. You
Mm-hmm.
just get y z.
Mm.
Modulo x just means remove all. Why do you remove the x's? Because x is the binding variable.
Yeah.
You see?
It is used.
Yeah,
It
it is
is
used.
bind.
So it cannot be free.
So we can substitute such. It is not free. Mm-hmm.
Yes. 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 And this is also, the author does this very nicely in the tree. So if you try to represent what we wrote, let's see, what was this? y lambda x x z. So in the tree format, this is going to be what? First, this is an application, right?
of y
So we
and
write a. So
mhm,
it's going to be y. Then it's going to be a lambda of x, right?
uh-huh.
And the lambda of x just goes to, sorry,
Application of
yeah,
x and
it's
z.
going to be, yes. So again, if you don't want to do all of this, you can just look at the free variables from here. What you do is you start from below, from here, and you look at, okay, x, z, okay, we take x, z. We, application, okay, application is fine, nothing wrong. But every time you cross an abstraction, a lambda, you have to remove the lambda term
Mm-hmm.
of the variables. So basically, whatever lambda you're doing, you have to remove uh, all of that from the below, right?
Mm-hmm.
So we took x z from here, but because we met lambda x, we cross out x, and then we pick out y. So it's just y z.
Mm-hmm. Yeah, that makes sense.
So yeah, every time you cross a lambda, you just ignore that binding variable.
Mm-hmm.
That's pretty much it. That's in that whole section. Yeah.
Yeah, that's the algorithm finding new
Yes.
variables.
Yes. Yes. And some definition is that if your lambda term has no free variables, then it is closed. It's called combinator. Apparently, I was surprised. Why is it called a combinator? Like, what's the rationale behind calling it a combinator? I don't know.
Combinator. It is just a combinator or with some name.
It's just combinator.
Hmm.
Yeah.
So perhaps all of the combinators have no free value?
Maybe, I don't know. Maybe we should do the experiment on Y combinator.
Maybe it is called a combinator because I don't know, you can combine it and it will not get stuck. I mean, if you're going to evaluate it, if the term has a free variables, then you'll get stuck. But with combinators,
Right, right. Yeah, it just swipes through it. There's nothing to get stuck.
So we call it lambda to the power of zero. How can we call it simpler? Lambda
It's lambda naught.
lambda naught. Uh-huh.
Yeah.
Three names: lambda naught, just combinator, or closed lambda term.
Yep.
Hmm.
Yep.
it is spelled as lambda naught, like that.
Yep.
Telegram.
Let me see the chat. Yeah.
No.
Yeah. Exactly.
Oh, uh-huh. Cool.
Yeah. So that's it. So we have just one section left, alpha conversion, and then we're done.
Yeah. You know,
This one
I
is a bit.
watched a lot of
Mhm.
videos about lambda calculus, and
Uh huh.
some of them were more advanced, I can say, from that point of view, from the past. But now I realize that they're not even close to this book, to the first 10
Right.
pages.
Yeah.
Well, that's what happens with YouTube videos these days. They try
Um,
to combine too much.
the sad part is that all of them doing the same.
Yep. Yep. It's just the fact that these things take time. You cannot do this in 10 minutes. You cannot process it mentally in 10 minutes.
We need more abstract, tuned brain to understand it.
Okay. Uh, let's see alpha conversion. So alpha conversion. Well, Kai, why don't you tell me? Like, what did you think about when you first came across this? Have you come across this before?
Yeah, on Russian Telegram chats, they're talking about some. It was actually Oleg Nizhnikov. Basically, he was talking about alpha conversion, and I looked it up on the Wikipedia. Before this, I came across this on chats. So basically, what alpha conversion about is that names just don't matter. You can define identity. For example, identity function with lambda x over x or lambda y over y. Names don't matter, and I think this is where the version indexes stem from too, because as long as the structure is the same, names don't matter.
Mm-hmm.
Like uh, we can, as we imagine, the lambda term is a tree. If the structure of the tree is the same, names don't matter. I mean, names don't matter in a sense that not just we can rename it randomly, but the bound names can be renamed without making it creating confusion. So here it gives. So basically, if the structure of the two terms are the same, and the so it gives an example. So a square function like x to x squared is equal to u squared. It just the difference is the name, but the structure and the thing that lambda term encodes is the same. So it is called so the terms that differ in the name, just differ in the name, but the structure and the so to say the wiring of the variables, like the binding of the variables is the same, but names are different. It's called alpha equivalent. So it gives a definition for the renaming. So the alpha conversion is based on the renaming. So you can just rename the variable in the term, provided that we follow two rules. The first rule is that the name, the name, I don't know the exact terminology, but so we have the name to be renamed and the value is going to be substituted. I mean, to the name that is going to be substituted. So if the new name, so let's say all the new name, so the we can rename the variables in a term. The new name is not a free variable in that term. Uh, Later on, in the chapter 1.7, it explains in details why this rule exists. So basically, it exists so that we don't accidentally uh, change the structure of that term. Like we can bind the wrong variable and just it completely changes the term. So basically, the new name should not be a free variable in the term, and the new name should not be a binding variable. So binding variable, as we discussed before, it is the name that is written near the lambda symbol. So um, it then later on gives a second definition. First one is about renaming, and the second one is about the alpha conversion. So basically, renaming properties, we can rename, but the structure remains the same, and both the old term and the new renamed term are alpha equivalent. And then the compatibility, I still am not sure about compatibility because we haven't given a clear definition for it. But so alpha equivalence is also reflexive, is also symmetric. So reflexive, the term after, so the two alpha equivalent terms are same by the reflexivity. By the symmetry, they can be swapped. Transitivity, as we discussed before, if L is alpha equivalent to M and M is alpha equivalent to N, then L is also alpha equivalent to M. So they're just definitions, given definitions. So there's also a third definition, alpha convertible and alpha equivalent. So if the M and if there are two terms which differ only by name, but if you rename the term, they can be the same. So it isn't called alpha convertible or the alpha variant or alpha equivalent. So basically, what we want to do is to preserve the structure and don't care about names. And I think, yeah, later on we'll just stop caring about names and we'll start using the version indexes or something. So yeah,
Yeah, yeah. I
overall,
think
just
yeah, I think
or
the compatibility part is just to ensure, that you can like apply things and abstract things, and the equivalence is still compatible.
mhm,
So it's like, you can have an equivalence that is M equivalent to N, and it will still stay equivalent if you apply some L on both sides, or you do some abstraction over Z. So
yeah,
that's what
because
it
the
is.
structure is the same.
Yes, the structure is the same.
Uh-huh.
Structure is the same. Yeah, so think of alpha conversion or alpha equivalence as like, so like every mathematical structure has its own object. So this is what category theory does. It's like, there are some objects, and there's, maps between the objects, the morphisms, and then there are the triangular laws, the unique mapping property of each category, right? So in the category of lambda terms, this is what we have. So this is like the way we can say that one thing is equal to another thing. So so yeah.
Despite instead of just how do I put it? Instead of just simply um, comparing recursively everything, we can just
Mm-hmm.
compare the structure instead of
Yes.
the name.
Yes. Yes. Yeah, and they just make one remark that yeah, because of reflexivity, symmetry, and transitivity, this is an equivalence relation. Equivalence relation is basically a special form of binary relation, basically a relation between two things um, that is very special. It is a structure preserving relation. That's the thing. So isomorphisms, bijective functions, functions themselves are all equivalent relations. They're all equivalence relations. So
Yeah.
yeah. Okay, so that is alpha conversion, I guess. Yeah, we have some examples. I think one thing that we need to still emphasize is that, so the condition for two things to be equivalent, right, is that you cannot have um, a binding variable and a free variable. Where did I lose this?
You mean the two rules?
Yeah, the two rules. Okay, this is
So the two rules are in the definition. So definition 1.5.1,
right,
provided
right.
that y is not a free variable in n and y is not a binding variable in m.
Yeah, yeah. I think this part needs to be a bit clarified.
Yeah, it is actually clarified in the chapter 1.7, if I'm not mistaken. No, 1.1.6, 1.6.
Right, when doing substitution. Yeah,
Yes, yes, yes.
yes,
Mm-hmm.
yes, yes.
So, for, I remember reading it thoroughly, that it was shown with examples that we can just destroy the structure if we don't follow these rules. I know
Right.
it is. Wait, it is in this 11th page, star one, star two, star three, in this chapter.
Yeah, the thing is, what I was trying to emphasize is that when this they say that y should not be a free variable in m, and y is not a binding variable, so it cannot be free in m, it cannot be binding in m. The reason is that because here what you're doing is you're replacing all the x's with y's. So if you get a free y that is free in m, what will it will be is it will get bounded by y, because this is lambda y, right? So lambda y will bound that free variable,
Mm-hmm.
and that is not allowed. So this is the thing, what this equivalence is doing is that you cannot rename things by changing their free or bound status. All the variables that were bound in the first name will be also bound or free in the second name. The free bound status cannot change. This is something to really note. The free bound status does not change, and this is the structure preserving part. It preserves the free and the bound variables. It does not touch them, and it will not touch them only if you have this condition.
Mm-hmm. So you can say that alpha conversion is basically a subset of triple equals, or they are the same, in fact.
No, so triple equals is equivalent. You see, so it's like syntactic identity. Syntactically, they are the same.
Ah,
Equivalence is that they're not syntactically identical, but they're equivalent.
okay, I get this. So
Yeah.
it's the reversed. Triple equals
Yes.
kinda subset of alpha conversion.
Yes.
Alpha,
Yes.
sorry, how's it called?
Alpha equivalence.
Equivalence. Uh-huh. So if we have two expressions or two abstractions which are alpha equivalent but with different variable name variables, you can
Hmm.
say variable names, they're not syntactically equal because of
Yes.
the variable mismatch.
Yes.
Mhm.
They're
Okay.
not syntactically identical, but they're equivalent. So like equivalence, like the three line equivalence, that's a special case of alpha equivalence. Do you get that?
Yes, totally.
Yes.
First I thought
Okay.
the reverse, the opposite one.
Yeah.
The triple
Yeah.
equal actually the real equal, but it
Yeah.
seems that no.
It's not. It's Wow, I think yeah, we've done up to 1.5. Yeah,
Yeah.
good job, boys.
It needs some practice, extra exercising
Yes.
to even better feeling all of these
Yes.
concepts. Yeah, really, thank you for these 2.5 hours. I got so much.
Mm, that's good.
And honestly, it's 10 pages of the book.
Yeah, yeah. Like this is like this reminds me of like when I was like doing mathematics for the first time. I was used to like just reading pages, right? But then when I started doing the things, it's like I'm like spending hours on few pages. So
Hmm.
it's very slow. But you learn it deep.
Yes. Actually, I'm starting getting comfortable with telling abstraction, application, and variable, honestly.
Yeah, that's good. That's good. You do it on pen and paper, maybe. Kai already does it on Lean, so he is like one level ahead of us.
No, actually, I also want to do it on Lean or Cog, or I have a book which is called Program Proofs.
Mhm.
It use prover called Daphne. I'm not started
Okay,
reading it yet, but a friend of mine bought it uh, from other country, in other country.
I see.
Yeah, yeah, getting very interesting, and will not cover
They,
the fully untyped lambda calculus yet.
Right. Yeah,
Yeah.
typed lambda calculus is going to get more interesting.
also, if
Mm.
you, Shahzad, if you want to, rehearse and, I mean, look up the definitions, there's another book called Lambda Calculus with Type. It is really helpful as a reference to
Mm-hmm.
I was also
to, to,
looking into that.
Can
to check
we
it out.
can you write the name to the our chat?
It is pinned already.
Ah, okay, okay. Thank you.
It has, as you call it, no bullshit introduction. So it has just definitions, a little bit of an explanation, definition, example definition, and so on and so forth.
Yep.
Okay. Um,
Yep.
I have one question.
Yep.
So we recorded 2.5 hours video. Can we make it public or it should stay private? What do you think?
I am fine with either.
Okay, what do you think? I'm
I'm fine with
thinking
it too.
I'm thinking about the future generation. The some curious minds that will open and hopefully get something.
Yeah, we can post it on Telegram channels or in YouTube too. So uh, we can post weekly or every 2 weeks, and
Yeah.
then in the end, organize a playlist and look back to what we
Yep.
were and so on and so forth.
Yeah, I'm already doing streams in our Uzbek language. So we will have a parallel streams in English. So I'm thinking marking the videos with flags and the prefix flags on title.
Sure.
Yeah, that's cool. And also, I'm thinking about making chapters, YouTube chapters, so you can easily navigate if you want to remember something.
That'll be lovely.
Yeah.
So the next meeting is going to be this weekend. I'm going out of town, so
Yeah,
I don't think
this
I have that
weekend
time.
I'm also very, very busy. Sorry.
Mm-hmm.
So when will you have time, Divya, next time?
Okay, so why don't we take 2 weeks? Um, like try to do the rest of the chapter, some exercises,
Mm-hmm.
Mm-hmm.
um, and then meet um, in like. Let me check the calendar. Um, First week of July. In any time in first week of July
Fine.
works.
We can
Fine.
pin this information.
Yeah.
Yeah. Okay, can you write and pin for the future?
Yeah.
And up to which chapter we should prepare? Does it matter?
Chapter 1.10, 1.10, and exercises.
Okay. July. Mm, it's my Telegram.
I can add that to goal. You already wrote it.
Yeah.
Mm-hmm.
Chapter 1 exercises. Nice, sweet.
Yeah.
So I think this is it. So
Yep.
thank you very much, Divya. It was really informative, and you are a really good speaker.
No worries.
That was really, really informative. I mean, I attended some clubs like this before, but
Uh-huh.
slept half of it. So yeah, but this time was really
I can
informative.
understand. I can understand.
Yeah.
No worries. Well, this was fun for me as well. So we'll meet on 1st of July and discuss more.
Mm-hmm.
Mm.
Big,
Until
big
then,
thanks to you.
thank
No
you very
worries.
much.
You too.
And also,
Take care,
your
guys.
your
Mhm.
voice is really close to, Tim Hansen, guitarist.
Tim Hansen of what?
His name is Tim Hansen. You can search on YouTube. His voice is
Okay.
very close to yours.
Okay. Thank you.
Yeah.
Yeah, okay. So I will try to post some notes that I'm taking of the chapters.
Mm-hmm.
Yeah, stay tuned for that.
Okay, big thanks.
Go and
Okay,
take
take
care.
care, guys.
Thank you
Yeah,
very
Good
much.
thank you.
evening.
Thank you too.
Good night.
Good night.
Yeah.
1:25 a.m. Yeah, bye. Shunaqa ish qilib.
Yaxshi bo'ldi.
Ha, chala inglizcham hatto sal odam bashara qilib oldim. Ko'p
Sezdim
praktika
mana.
yo'qda, praktika yo'qda. Mana shunaqa praktikadan ko'proq kerak bizga. Men hozir o'ylab turibman, videolarni hozir YouTube kanalga qo'yaman. Buni ham zapisni to'xtatib hozir. Har bitta nonni boshiga bayroqcham qo'yib chiqaman endi, O'zbekiston bayrog'i, keyin men bu bilmayman, British qo'yamanmi?
Inglizcha.
Shu language'ni bilish uchun.
Mhm.
Zo'r bo'ldi lekin. Katta rahmat. Qayerdan topgansiz bilmadim. Mahmudovnani lekin bopladingiz.
Mhm.
Lekin tushunishni boshladim, eng qizig'i.
O'zingiz tiqib qo'ygandan keyin dashboard ham yo'qolasiz, organ ham yo'qolasiz, tashlab qo'yasiz. Qancha
Вот,
videoda
mana shu narsa lekin
ko'rgansiz.
menga yoqdi. Gruppada borku, juda yoqdi. Hamma o'zini fikrini aytishni boshlaganda, men tushunmagan narsam tushunishni boshlayman. Nimadir so'rasam, уже keyingi chapterda bor ekan deb, free and bound variables ham tushundim, в принципе. U three representation cho'tki yoqdi. Lekin men bu kitobcha chiqarib olgani вообще cho'tki bo'ldi-da.
Ha, qaychi. Men kitobni lekin hali ham tuzatib bermadi lekin. Berib hali yo'q.
Sub 3da boshida qiynaldim, sub 3 tushunarli bo'ldi. Variable application abstraction более-менее okey. Mana free values вообще четко tushunarli. Просто anavi exclude qilib ketamiz. Pastdan tepaga traverse qilib. Alpha conversion plus minus tushundim, lekin men examplelardan ustidan ishlashim kerak. No basic rule nima? Agar biz bound variable bilan free variable ni rename qilmasak, то есть rename qilmoqchi bo'lganimiz o'sha bound yoki u bo'lmasa, bemalol. Yana bitta narsa, mana bu alpha equivalence, bu kattaroq set deydimi? Короче, 3 ta equal, triple equal bu subset of alpha equivalence da. То есть mana shu narsa hozir xayolimda aylanib yuribdi.
Janob murakkablashadi. Misol uchun oddiy misoldan ko'rsak bo'ladi. Ya'ni get user by id da parametrni xohlasangiz id deb nomlang, xohlasangiz id number deb nomlang. Baram logika bir xil qolaveradi-yu.
Bu alpha
Yaxshi,
equivalence da. Xuddi shu.
Xuddi shunaqa. Juda ham sodda narsa. Dasturlashga o'xshab parametrlar qanaqa nomlamang, ichidagi strukturasi bir-biriga bog'liqligi.
Endi eng qizig'i triple equal'i bu masalan ORM ishlatasiz-ku, bir xil expression yozsangiz tagida bir xil SQL kelib chiqqandek gap.
Shunaqa.
Qo'pol qilib, SQL ham yaxshi fikr emas, chunki hozir sintaksis o'zgarishi mumkin, lekin qo'pol qilib aytganda shunaqaroq narsa. Bir xil narsa chiqadi.
Strukturani ko'tarib turadi. Bir xil strukturani ko'tarib turadi. Bunday bo'lsin, lekin bir xil logikani ko'tarib, bir xil struktura bo'lyapti. Afrika. Hali vaqt keladi anaqa mana shunaqa x, y degan nomerlarni chop tashlab, o'rniga raqamlar ishlatiladi. Differential indekslar deyiladi, oldin aytganimdek. Umuman keyin osonlashib ketadi. Endi o'qishga qiyinroq bo'lishi mumkin, lekin ancha osonlashadi.
Ha. Bo'lsa, men sekin yuray. Sizga rahmat. Divya bratga ham rahmat. Mana kontent qilamiz. Необычный kontent qilamiz.
Exclusive short content.
Ha. Mayli, rahmat. Yaxshi.
Yaxshi.
Hop.